Okay, so and plasma is that matrix. And again, if you go back and watch the video from Tuesday, or if you even just viewing the slides or looking through OpenStax, there I have a couple charts in the slideshow that break down what's in plasma. And generally, we would see the bulk of plasma being water. All right. So, and again, there are ranges with blood. So with plasma, we typically see roughly 55% of blood volume being plasma. So, and out of that 55% that's plasma, about 95% in that range is going to be water. So, you could say then roughly 50% of blood is just simply water. So the other aspects of plasma we see are what we call plasma proteins. These play different roles. Mostly they play roles when it comes to osmotic balance. So that gets into physiology stuff. So I'm not going to get into osmotic balance right now. So we'll revisit plasma proteins like albumin is one you've maybe heard of. Alba means white. So albumin means like a white protein. So it kind of gives plasma a creamy color or appearance. But anyway, like I said, in advance, we'll look at albumin and other plasma proteins. There's something called immunoglobulins. So you've maybe heard of those. Those are, in essence, they're like antibodies. So immunoglobulins are abbreviated IG, and then we'll look at several different immunoglobulins. We'll look at some next week, actually, when we get to the immune system. So anyhow, plasma's got primarily water, and the rest is plasma proteins, and then a little bit of certainly all of the nutrients, right, that we consume. Those are going to be contained in plasma: vitamins, minerals, carbs, proteins, fats. That's all going to be contained in plasma. We're going to find waste products too, of course, right? So it's groceries in, garbage out. So remember, right, the whole purpose of blood is to be able to deliver substances of whether it's those macromolecules we just discussed, or vitamins or minerals. Hormones are going to be found in plasma, of course. Enzymes are going to be found in plasma. So blood is the delivery system, kind of the delivery medium for all of these nutrients. And then, of course, we would find some gases contained in plasma as well. Plasma and blood is also it's the trash system too. We'll see coming up a little bit today and a lot bit next Tuesday, the vascular system using blood to not only deliver groceries, but to take away or remove wastes. So anyway, plasma, that's where a lot of the action is. Now, the cellular aspects of blood are going to make up roughly 45%. So the rest of your blood, so about 55% plasma, roughly 45% what we call cellular material, or everything else. That's primarily going to be made up of red blood cells. So out of the 45% cellular portion of blood, we do see 99% of that 45%. That's a lot. And I know it's math and numbers, but in percentages and ratios. But anyway, out of the 45% that's cellular, 99% of that 45% is red blood cell. And that's what we call the hematocrit. So in a clinical setting, we would want to know maybe what the packed cell volume is, or what the hematocrit is. And that's in essence what the red blood cell percentage is. So usually we see a hematocrit around 45. Now for women, the range is maybe 37 to 46, 45. For men, it's maybe 42 to 48 or something like that. So generally speaking, those are the range around 45%. And again, that is simply going to be the red blood cell percentage. So relative to plasma. So it's basically hematocrit is kind of like a ratio of plasma, of red blood cells to plasma. So 45 red blood cells, 55 for plasma. So if hematocrit is lower, so say 30 or 35, then that would mean to the rest of that to 100% is going to be plasma, more than likely. So that'd be 70% plasma, 30% red blood cells. Okay, that would be a low hematocrit. So what that would tell me is that I might have a situation where there's some anemia going on. There's not enough red blood cells. Red blood cells deliver oxygen. So if I don't have enough red blood cells, I may not have enough delivery folks to bring oxygen to the cells. So that can lead to low energy levels. So if a patient comes in, they're normally fairly, healthy, and they've been experiencing unexpected and the unfathomable kinds of energy level depletion, we may that's a problem. So we're maybe hopefully it's a simple problem to solve, but we're going to probably run some blood tests, maybe see if we find maybe they have some anemia, they don't have enough red blood cells relative to plasma. The other thing we could see is a high hematocrit. So it could be like 60. So you have 60% red blood cells, 40% plasma. That is going to be an issue too. We've got blood now that's too thick, it's too viscous, it's not thin enough. So too much cell, not enough plasma. So that's a dehydration scenario. So we're very concerned that's going to put a lot of strain on the kidneys. That's going to put a lot of strain on the heart because it has to pump something maybe more viscous, like the viscosity of a blizzard, a Dairy Queen blizzard, versus pumping something more like the viscosity of oil. So the heart would have to work harder if the blood is thicker. So oftentimes that's why blood thinners are given, is to kind of help with some of the load that's placed on the heart. If the heart has to pump thick blood, then it has to work harder. So anyway, hematocrit can tell us quite a bit of information potentially about the individual. Now, staying on red blood cells for just another second, they also have, and we looked at this Tuesday, something called hemoglobin. And hemoglobin molecule, you want to remember, has four, or recall, or put in your memory bank that each hemoglobin can connect with four oxygen molecules. Okay, so 4 oxygens for one hemoglobin. Now, one red blood cell has roughly 250 million, hemoglobins. So one red blood cell can carry roughly a billion oxygen molecules. So, and red blood cells are extremely tiny. In the tip of your finger, you've probably got close to 20 million red blood cells, each one of those carrying a billion. We're getting into some big numbers, right? A billion oxygen molecules. So you can imagine oxygen is extremely tiny as well, and there's a lot of it, but we do have to keep it balanced. And it's the red blood cells, along with bone, right? Bone marrow play a role. And then we'll see later on that the kidneys play a pretty big role in helping to maintain red blood cell count. So anyway, hemoglobin. We can also test that on the clinical level. Hemoglobin is going to give us a more specific number or count of not necessarily red blood cell percentage, because that's hematocrit, but we could get a more of a detailed description of hemoglobin, how much hemoglobin specifically is available, and thus how many red blood cells might be available. Okay, because we could have a situation where red blood cell count or hematocrit, the percentage, hematocrit looks low. It's like a 30%, and plasma would be 70%. On the surface, that might look like we have an anemia type of a situation. But in reality, we may have the the proper number of red blood cells. We may have the proper amount of hemoglobin that's making up that 30%. We just have an excess amount of plasma. For some reason, the ratio has been altered by an increase in plasma. So if red blood cell numbers and hemoglobin numbers are normal, but I increase plasma, that will throw off the hematocrit. So again, that's getting into a little bit of clinical-y stuff, and but I think you can kind of see maybe the numbers and how that may look. Now, next Thursday, when we're doing, or when you're doing some of your blood typing and some of your work on your portfolio and lab assignments, I'll pull up a sample CBC readout so you can kind of see what some of these numbers look like. But again, hemoglobin is separate from hematocrit. I hope that makes sense. Okay. And if I have excess plasma that's making my hematocrit look low, then that could be a kidney failure issue. I'm not that's a fluid problem. Hemochromatosis. Lori, I'm not 100% sure. I know that has to do a condition of, let's see, chroma would have to do with color. So not 100% sure. I'd have to Google that
Well,
one.
the reason why I ask is because we have patients that have hemochromatosis, and so obviously they have an elevated either hematocrit or hemoglobin. But I'm wondering if it's actually both, or if they have elevated a lower percentage of or a higher percentage of hematocrit and hemoglobin, or if it's really one or the other. So I wondered if they had a role in playing with hemochromatosis.
Well, we can find out. Hemochromatosis.
Because those people have to donate blood, in which they get rid of red blood cells, but then I just don't know if the hematocrit is also involved.
So
Yeah.
too much iron. So that's going to be a hemoglobin is going to be high. Iron overload, intestines absorb, and hemochromatosis, your body absorbs too much, has no way to get rid of it. So yeah, on a blood test, I would say the hemoglobin count would be high. Well, heme, by the way, means iron. So each hemoglobin has 4 irons. Now, maybe it's the opposite. Maybe there's not I would think the iron load is in the hemoglobin itself. It talks about the foods you eat usually cause inherited rise from iron. Oh, so diabetes, abnormal heart rhythm, removing blood from the body. Yeah, so so all of that iron is in. So their hemoglobin would be high, and their hematocrit likely would be high. Both, definitely their hemoglobin count. Fewer than 200,000 cases a year. Yeah. Hmm. I
And
bet
funny thing is,
I
I
bet
think
it's
it's
going up with more diabetics and that, right?
and I think it usually it affects men obviously more so than women.
Okay, sure. Nice. Cool. Yeah, and it's heavy metal toxicity. I mean, iron's a heavy metal. We need it, obviously, but the RDA for iron is very small. You can see why. And plus, we're producing red blood cells constantly. Now, we could also potentially see this in like a bone marrow cancer patient. So we would see hematocrit levels really high. Um, we would see hemoglobin levels equally, or I guess concurrently high, or subsequently they would be high as well. Because yeah, why would we have so much iron? Well, maybe we have way too many red blood cells, and so then we'd be wondering about bone marrow cancer. But yeah, the intestines absorb the right amount, so maybe there's an issue with the absorption of the intent. And it talks about type 2 diabetics. So there's got to be some sort of a link with how insulin and glucagon also function with iron delivery. All right, so let's cool. Yeah, hemochromatosis. Okay, go back to captions. Okay. Let's see.
No.
Whoa. All right. Erythros. So anyway, moving on. We've got a lot of fish to fry. Leukocytes next. White blood cells. We'll see these next week when we do immunity. We do have 5 different white blood cell types. Granulocytes. So under a microscope, we would see little tiny granules in the staining, and these are the fill group. So they're going to be neutrophils, which are the most abundant of our white blood cells, and then basophils and eosinophils. Now, again, white blood cells or leukocytes, their primary role is related to immunity, of course, and part of that that immune system is obviously, like, destroying and going after pathogens, right? Infections. But beyond that, we also rely on white blood cells in the immune system to kind of vacuum things up. They help with debris pickup. They're kind of like the janitors or the custodial system I think they call them uh, maintenance engineers of your blood. So there's a lot of debris, frankly, in interstitial fluid, in plasma, and so white blood cells, they do have the ability to, by the way, to leave a capillary to go into the interstitial space, or what we call it, the extracellular space. But anyway, they can leave and go kind of engulf and clean up stuff that maybe is en route to a cell, or even cell debris from a cell going through like apoptosis or cell death. So anyway, leukocytes help to kind of keep your blood clean. Uh, in addition to certainly getting rid of pathogens, and the type of white blood cell, or I guess the job or the function of the white blood cell is maybe slightly different from white blood cell to white blood cell. But for the most part, the fill group, they are part of what we call that kind of that innate immunity, or that born in immunity. So they're just part of your basic immune system, which again involves kind of cleanup. Now, agranulocytes, these are going to be your lymphocytes, and then your monocytes. Lymphocytes are going to be the second most numerous behind neutrophils. So neutrophils and leukocytes are your most numerous. The rest are pretty small in number. So anyway, agranulocytes, they're more specific, especially the lymphocytes. They're kind of in their own category. In fact, we have a whole system called the lymphatic system. So we'll come back to lymphocytes then. Thrombocytes are platelets. Those are responsible for hemostasis and forming what we call a platelet plug. If we have some sort of a breach in a vessel, we need to plug that breach. Basically, when blood vessels are kind of lined with epithelium, and then that's kind of sub area of connective tissue has a lot of collagen fibers. So if we have a tube, and that tube breaks, or there's a breach or a rupture, there's going to be little bits of collagen fibers that are going to be kind of exposed where that breach in the vessel is. Platelets are going to kind of congregate. I think they call it platelet aggregation. They like kind of get caught in their platelets are kind of sticky and jagged edged anyway. They're very tiny. And so they're just going to get caught in the collagen webbing from the breach in the blood vessel. So that's going to kind of stop the blood from leaving. And then at the same time, we've sent some triggers to the nervous system and endocrine system are now, they've been triggered. So we're going to see some anti-inflammatory drug chemistry coming. And then we're going to see what's called clotting mechanisms. So we're going to build kind of a bigger clot. We call it coagulation. That's going to involve something called fibrin and thrombin. And what fibrin and thrombin and coagulation, those chemicals and proteins are going to not only adhere to where the platelet plug is, but they're also going to kind of form and encourage like new cell growth. And eventually that becomes a blood clot or a thrombus. And then we have specialized, thankfully, we have specialized chemicals that we'll look at a little bit more next semester that are going to come in and kind of eat up and dissolve the clot. So we have normal, natural clot dissolving mechanisms in our bodies. Well, if we have too many clots and not enough chemicals to dissolve clots, that can happen certainly with age as well. Certain medications can kind of promote this. Sedentary lifestyles promote that. So we have to be careful with certain methods of physical therapy, dealing with the calf muscles or the gastrocnemius, soleus. That area tends to be, and behind the knees, those are where tiny thrombus issues can build up. So when a thrombus kind of breaks off from a blood vessel and travels, they call it an embolus. So an embolism is when the embolus stops traveling, and it usually stops traveling when it gets to the lungs. So we'll see why in just a few minutes. And then lastly, we talked a little bit about blood typing. And again, next Thursday, I'll go back through some of the blood typing. There's an exercise and kind of a virtual blood typing activity that you can do that's in the portfolio. Next semester in advanced, I do another kind of a little more detailed, but not too much more detailed, virtual blood typing again. So we do a couple of virtual serological tests in advanced. So yeah. Um, Probably why so anemic patients with higher platelet counts. Okay, so what are normal first of all, normal platelet counts um when it comes to percentages of total blood volume. Generally we should see less than 1% of your total blood volume being platelets. Same with white blood cells. I want to back up even one more about lifespan. By the way, red blood cells have a lifespan of about 120 days. And again, they make up roughly 45% of the blood. White blood cells, on the other hand, have a generally a fairly short lifespan, sometimes minutes, hours. Some white blood cells do live a long time, some of the more specific immune fighter. So anyway, we'll talk about some of the differences in white blood cell lifespan next week when we get into the immune system. Now, yeah, platelets, also less than 1% of the total blood volume. Now, the actual numbers of platelets is extremely high normally because they're so tiny, not extremely high. It's not as high as, red blood cells, but, you might find 50,000 platelets, per uh, cubic, uh, um, cubic millimeter. So a tiny area, you're going to see maybe millions of red blood cells, tens of thousands of platelets. Now, someone who's anemic is going to have lower red blood cell count. They're going to have problems oftentimes with some of the plasma proteins that also go with anemia. One of these plasma proteins is called fibrinogen. And so fibrinogen helps with kind of the repair of blood vessels. And so along with being anemic, we generally are going to see some issues with blood pressure, maybe some issues with micro tears, coagulation, necessitating more coagulation. Now, so more platelets means we need more coagulation for some reason, or more platelet plugging. So, due to the anemia, there are going to be different pressure, there are pressure problems. And so we're going to see a lot of times these show up at the capillary networks, where we're going to see broken capillary walls that have been repaired. Now, these don't necessarily show up maybe on the surface, but internally, we could see more platelets due to more damage to blood vessels because of, in essence, we've got a solution. The percentage of the solution, we call blood's a colloidal suspension, but it basically looks like a solution. And so that balance and osmotic pressure changes that occur from either too much of something or not enough of another, alter the pressure and the so anyway, I think that kind of gets into it. So yeah, if you have anemia, you're going to have blood pressure issues because of the ratios of plasma to red blood cells. You're going to have more fluid, and so what we're going to see, the kidneys typically have to work harder within a patient with anemia. We might see the liver also working harder. Platelets produced by red blood cell or by bone marrow. I believe the liver also can play a role in some of that. Uh, so anyway, yeah, more damage in the micro levels to these filters because of basically blood that's a different type of viscosity. All right, so A, B, O, and RH. We'll get into blood typing more next week. And we do it next semester too. So if you're shaky on blood typing, we'll try to clear it. We'll watch the video from Tuesday, and then read through it a little bit in chapter 18, and then we'll go from there. All right, so let's get to it. The heart is next. Now, as we segue from blood and the medium in which we're trying to transport groceries and pick up and eliminate waste, we have to be able to pump that blood. It's not going to just travel through the body because of I don't know how it would. I guess we do see some venous blood move through the body. In fact, going back to the heart because of the location of the veins relative to the skeletal musculature. So the heart actually is similar in structure and makeup on the cellular level. There's a few differences to skeletal muscle. We do see striations just like we do with skeletal muscle. So there's definitely contractibility or contractility possible, right, with the heart. So we're going to see heart contractions. It's going to eject blood. Now, again, without that pump, well, blood would become pretty stagnant. So when we look at the heart, before you ever took A&P, you probably knew that, right? You probably knew that the heart was a pump. Now, the degree to which it pumps and the complexity therein is what we're going to go through tonight. Now, the location of the heart, the connection of the heart with other body systems is evident right away. We look at the location, and the first thing we notice is kind of this hash mark or dashed line. This is what we call the mediastinum, and I think this term is familiar to most, if not all of you, from the beginning of the semester when we talked about body cavities. We looked at the thoracic cavity, and the mediastinum was the area of the thoracic cavity that it's kind of a subregion where we find it in the middle near the sternum. So in essence, mediastinum has to do with down the middle and relating to the sternal region. So we do find more than just the heart in the mediastinum. We find what are called the great vessels of the heart. So we'll look at these in more detail. We'll give them names in just a few minutes. But we also see a part of the respiratory system. We can see, let me get my pointer on. There we go. We can see the trachea here. Mm, mm. There's a thyroid gland here, but we do see the trachea within that mediastinum, and just behind or posterior to the trachea, we're going to see the esophagus. So the esophagus is also part of the mediastinum region. The trachea is part of the mediastinum. We see some major blood vessels, and then of course the heart. So anyway, that's the kind of the first thing we notice. The second thing that you notice as we travel through is we do have this a lot of color going on. We've got the blues and the reds, and we know blue always has to do with low oxygen blood, and red always has to do with highly oxygenated blood. So oxygenated, low oxygen for blue. They don't necessarily mean artery and vein. So we'll talk about that in more detail coming up. The other thing we notice about the heart itself, it is a little bit left justified or left of center. The majority of what we call the left ventricle is going to be located and taking up, in fact, taking up a part of the space where the left lung would take up. So when we get to the respiratory system, we do actually see the left lung is slightly smaller than the right lung, again, because of the positioning and location of the heart. We also notice, and again, all of this information, all of these descriptive terms, we'll look at these in more detail. This is just kind of an intro slide. I don't want to spend much more time on it, other than showing you the position of the diaphragm. And then we have the pericardium of the heart, the sac that surrounds the heart, connected with the diaphragm. And then we'll also see in a couple of weeks when we get to the respiratory system that the lungs are connected with the diaphragm as well. So anyhow, just kind of showing you the central location within the thoracic cavity that we do find the heart, and then its proximity to the lungs, which is going to come into play and be very important in just a few minutes. Now, there's a small section in your book or in your OpenStax text on CPR. So again, if you haven't done your CPR, you will at some point, your CPR training. Hopefully you never have to do it or perform it, but you will have to perform it on a dummy and your CPR training. So they'll discuss kind of the tracing and placement of the palm. And then again, we want to be generally right on the center of the sternum and pushing directly down. Now, where that lines up happens to be between T5 and T9 of the thoracic vertebral group. So anyway, that's just a little side note there. You can certainly look through. This next slide is this is going to kind of, I guess, be a little bit of an introduction to the vascular aspect of the cardiovascular system, because it is one word, right? Cardiovascular system, but we do kind of compartmentalize cardiac and then vascular. Now, next Tuesday, we'll get into more detail about the vascular aspect, but I do want to introduce you to a couple of the key features of the blood vessels of the body, especially because the heart and its blood vessels, that network they're connected. It's a circuit system that is closed. You can see that all of these tubes are interconnected, and we have the heart being kind of that center cog or pump. Now, again, we have blue meaning low oxygen. Now, and we can see all of this blue blood traveling to the right side of the heart. And again, I know it's on the left side of the screen, but we're looking at as if we're looking at a patient. So this is the patient's right side. So the right side of your heart too is going to be where the low oxygen blood is going to be traveling through. So we can see blue traveling through the right side of the heart and then leaving. And then that blood goes over to the lungs. So we'll talk about all this in more detail shortly. And then on the left side of the heart, we can see the red oxygenated blood coming into that side and then traveling certainly out to the body. So when we go a little bit deeper into analyzing the heart structures, we're going to take it in right half and left half. Okay, so right half of the heart deals primarily with low oxygen blood. So we're going to see blue representing the right side of the heart and what goes on. So the total opposite of the politics spectrum, right? Or the political spectrum. Right side there is red and left side there is blue. Well, when we're talking about the stuff that really actually matters, which is A and P, right side of the heart is actually where we would see blue represented, low oxygen levels. Now, this right side of the heart is receiving blood from the body. So we're going to see the terms veins. Okay, arteries, and capillaries coming up. So, first off, veins always go toward the heart. So, veins always toward. So, we can see follow these arrows. All of this blue blood is dumping into the right side of the heart. These are going to be veins that are bringing that blood to the heart. Okay. So, venous return is something we'll talk quite a bit about next semester. Venous return. Okay. So, when we where are we going with this blood? Well, if it doesn't have oxygen, we probably need to send it somewhere where we can get oxygen, and that would be the lungs. So, the right side of the heart is going to pump the blood over to the lungs. So, as we saw in the previous slide, lungs are very close to the heart. So, we don't have far to go. We see that right side of the heart pumps blood to the lungs, and those vessels that are leaving the heart or going away from the heart are going to be called arteries. So arteries always away. Okay, just remember that. Arteries always away. Then what about veins? Veins always go toward then. Okay, arteries always away. You'll never go wrong if you remember that. Arteries always away. So these arteries are going away from the right side of the heart, traveling over to the lungs. Okay. And then at that point, we can see what are called capillaries. We have capillaries. These are going to be pulmonary. There it is over here. Pulmonary capillaries. And pulmonary means lungs or relates to the lungs. So capillaries are the third vessel type. So we've seen veins going toward, arteries going away. Well, what about where arteries and veins or veins and arteries, what about where they meet up and come together? We call that a capillary network or capillary bed. So um, arteries and veins, generally, we shouldn't see anything leaving the bloodstream. Okay, these are contained. So they're just tubes that contain blood where we're transporting nutrients or eliminating waste or transporting gas and eliminating waste gas. But we're not going to see anything leaving the bloodstream or going into the bloodstream when we're dealing with veins and arteries. Okay, very important to get that. So, how do we get anything into the bloodstream or out of the bloodstream? We need what's called a capillary network. So, capillaries are, we'll see next week in more detail. We'll look at the actual differences in diameters and structural features of capillaries versus arteries versus veins. So I don't want to get the cart too far ahead of the horse, nor do I want to spoil the surprise for next Tuesday. But I will say that capillaries are where exchange takes place. So the whole point of this, and the whole point of this and breathing and all of that stuff is to get the nutrients to the cells of your body. So how do I get oxygen to my cells? How do I get carbs, proteins, fats, vitamins, minerals, water? How do I get all that stuff to my cells? I got to get it into the bloodstream. So in my intestinal area, or if it's oxygen in my lungs, I just have to bring oxygen in. That oxygen is going to make its way into little tiny areas where we're going to find a lot of capillaries, and the oxygen is just going to diffuse into the bloodstream through those capillary walls. So capillaries do have walls that are permeable. So anyway, gases. So in the lungs, we see gases being exchanged: carbon dioxide out, oxygen in. So that's what's going on with these kind of webby looking mesh, kind of red and blue coming together, making purple. That's going to be capillaries. That's where any type of exchange takes place. Now, we're going to see capillaries everywhere, everywhere in the body. If I need us, and all cells need to eat. So how do I get a cell oxygen? How do I get a cell amino acids? How do I get a cell glucose? Well, I need capillaries to be near the tissues and near the cells. So as soon as I get oxygen delivered to a tissue site, oxygen diffuses out of the bloodstream in the capillary network and makes its way into your cells. So capillaries are where all of the action takes place. Arteries and veins, those are just the tubes that deliver things away from or to the capillary networks. All right. And the heart's there right in the middle of all the action doing the pumping. All right, so left side of the heart receives. So this is a vein. Veins always go toward. So from the lungs, we're going to go toward the left side of the heart, drop off that nice, rich, oxygenated blood, and then we're going to pump that blood out up to the upper body and down to the lower body. We're going to see gas exchange, nutrient exchange, and then just keep cycling it back. So right side of the heart, blue blood, part of that pulmonary circuit. So we start at the right side, go out to the lungs, come back to the left side. That's the pulmonary circuit. When we look at the systemic circuit, we're leaving the left side of the body or of the heart, taking all that blood to the body, and then coming back to the right side. So that's a little bit of your intro to path of flow of blood through the body. We'll look at it a little bit more next Tuesday, and certainly spend a lot of time on that next semester. Now, let's give some names to some of the structures of the heart. First off, when we look at the right side of the heart, again, we do have two veins coming into the right side of the heart. Those are going to be called superior vena cava and inferior vena cava. So from the upper body, we're going to be dumping oxygen or low oxygen blood into the right side. And from the lower body, so from below the heart or inferior to the heart, we're going to be bringing blood to the right side as well. So low oxygen blood coming to the right side of the heart. The first chamber that we see is going to be called the right atrium. Okay, the right atrium is the first chamber that low oxygen blood goes into. And then we have what's called an atrioventricular valve, or a tricuspid valve. And this is maybe the first time we've seen the word valve this semester. A valve prevents backflow. So whenever we see a valve anywhere in the body, we'll see them in other spots. That means that we're trying to prevent backflow. Valves prevent backflow in your car, in your plumbing, in your house. So that's generally what a valve is for. So Which makes sense, right? As we're if we're moving blood into the right side of the heart, the goal is to get it to the lungs. We don't want to back up the line. So anyway, the right atrium is going to dump into the right ventricle. The blood's going to pass through the tricuspid valve or right atrioventricular valve, or what they call the AV valve. So AV valve, atrioventricular. As we leave the right ventricle, we're going to pass through another valve. So we have gone chamber, right atrium, valve, tricuspid, chamber, right ventricle, to another valve. This one is what we call the pulmonary valve. This one tells us where kind of we're going with this blood, right? We're in that pulmonary circuit. So you also see the word semilunar. Semilunar means kind of partial moon or half moon. Okay, so we've got chamber, valve, chamber, valve. That's the same organization that we're going to see on the left side of the heart in just a couple of seconds. Okay, so veins dumping into the atrium, valve into the ventricle, and then another valve. Okay. Now, where are we going? We're going into the pulmonary system. So, as that pulmonary valve opens, we have what's called the pulmonary trunk. And that pulmonary trunk is going to lead us to what we call the pulmonary arteries. You're going to have left pulmonary arteries and right pulmonary arteries, again, bringing blood and distributing it to each of the lungs. And again, these are arteries because they're bringing blood away from the heart. Now, the pulmonary arteries are the only arteries in the body that are delivering or carrying blood that's low in oxygen. Pulmonary arteries, only arteries in the blood that are going to be labeled blue or low in oxygen. Okay, so they're taking blood over to the lungs. And then we get the gas exchange. And then what do? Send that blood. Now it's rich in oxygen, so it's represented as being red. It's going to come into the left atrium via these pulmonary veins. Veins always toward the heart. So pulmonary veins bringing blood to the left atrium. Now, these are the only veins in the body that are rich in oxygen or high in oxygen. So if you're ever asked what artery or what vein is the only blah, 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 something to do with oxygen, then it's probably pulmonary. Pulmonary is the only exception for either item. So only pulmonary arteries they're the only arteries carrying low oxygen blood. Pulmonary veins, the only veins that are carrying high oxygen blood. So anyway, veins always toward. Okay, pulmonary veins coming from the lungs, highly oxygenated blood into that chamber, the left atrium. And then, just like we saw on the right side, chamber, valve, chamber, valve. So, chamber, left atrium. Valve is going to be the left atrioventricular valve or left AV valve. They also call it the bicuspid valve or the mitral valve. We do see mitral valve. Uh, um, Sometimes it doesn't function the way it should. They call it a prolapse, mitral valve prolapse, and they go in and sometimes they use cadaver, sometimes they use pig, but anyway, they can fix sometimes they just use synthetics to fix your mitral valve. That's bad if the mitral valve's not working because every time the left ventricle, our next chamber, every time we eject blood from the left ventricle to go into the aorta, past the aortic valve, if that mitral valve is dysfunctional, we may get some of that oxygenated blood actually going back into the left atrium. That's going to cause a backup toward the lungs. We have congestion going on. Okay, so we don't want to have traffic congestion. We need to keep the line moving. So a bad valve can cause backflow. All right, so anyway, left ventricle. Notice too the ventricle area. I know this is diagrammatic, but the ventricles are the more muscular chambers of the heart. These atria are not very muscular, and again, why would that be? We only have to move blood from here to here when we're dealing with atrium to ventricle. So these guys don't have to pump very hard. So if I need to move blood from right here to blood in here, this chamber does not have to pump very hard. In fact, if I just open the trap door and then give this a little bit of a squeeze, I'm going to get the blood down into the ventricle that I need. Now, when the ventricles go to contract, right, the right ventricle's got to eject blood actually out of the heart over to the lungs. The left ventricle has to pump blood ejected out to the whole body. So we do see the ventricular walls a lot thicker. I've got a slide coming up that shows that in just a few minutes in more detail. Okay, so anyway, as we leave the left ventricle, we're going to pass through the what they call the aortic valve, and again, chamber, valve, just like we saw on the right side. As we leave the left ventricle, we're going to enter into the aorta. The aorta is the largest artery of the body. It actually travels from right here in the heart, and it goes all the way down, and just right around the umbilical areas where we start to see the aorta kind of fork and go over to the left side, right side. So anyhow, whew, that's a lot of stuff. I do realize that. But again, if you just take it in right side, left side, so right side and left side are nearly identical, just a few subtle differences. They both have a chamber at the top called the atrium. They both have a valve called the AV valve or atrioventricular valve. And then they both have another chamber called the ventricles. As we leave the right one, we're going out to the lungs. So that valve we call the pulmonary valve. As we leave the left side, we're going into the aorta. So we call that the aortic valve. And again, right side is blue blood coming from the body, heading over to the lungs. Right, so that's the right side of the heart. Left side of the heart is blood coming from the lungs. It's full of oxygen being pumped out to the body. So that's kind of the long and short of the basic structural features of the heart. I'm only going to add a couple of more to this, but other than that, we're pretty close to being done for the night. We have more. We'll add more to this, over the next week and a half or so. But this is kind of your introduction to the basic structures of the heart. Now, we have to have an electrical system that we're going to add next semester to that. We have to have a system that supplies and feeds the heart itself, right? We've only talked about blood going into the chambers, blood leaving the chambers. Well, what about the heart itself, right? It's got to get fed. That circuit system we'll talk about next semester as well. We're just giving you the basic structures. Now, this next slide goes into the pericardium. We've talked about the pericardial sac before. It's kind of a double layered membranous sac that surrounds the heart. We see that the visceral aspect, the visceral pericardium, is going to be right up against the heart itself. So we'll get there in just a second. Let's go from deep to superficial with this one. So from deep, we're actually inside the chamber here, where my pointer is. We see endocardium is going to be the innermost lining. So the chambers of the heart are lined with endocardium. And then just deep to the endocardium is that thick myocardium. Okay, the myo means muscle. So this is the heart muscle. And then we have what's called the epicardium. So that those prefixes shouldn't be that unfamiliar. We've seen endo meaning inside, epi meaning upon. We've seen those several times really this semester. So the epicardium is going to be the layer, the outermost layer of the heart itself, not the pericardium. Now, that epicardium is considered to be the visceral layer of the pericardium. So in essence, it's the outer layer of the heart muscle is also the visceral pericardium. All right. And then there's a little space called the pericardial space or pericardial cavity. And then superficial to that is what we call the parietal pericardium. So you have the visceral pericardium, parietal pericardium. They make up combination wise the serous pericardium. And remember, serous has to do with a serum. When we looked at membranes, we saw serum or serous. That just implies there's a fluid and therefore implies there's a cavity, okay, for that fluid. And then the most superficial aspect is the tough pericardium we call the fibrous pericardium. So the fibrous pericardium and the parietal pericardium, difficult to tell the difference. Like if we were in lab together tonight or next week, probably tonight would have been the night where we would be pulling out the pig hearts, which still have the pericardiums, and we would be cutting through the pericardium so you could see, then you'd be dissecting the hearts. So damn COVID, why I oughta, but I won't, because I can't. What the hell am I going to do about it? Well, we can all do our part, right? And do what they've been telling us since March: social distancing, wear your mask, wash your hands. Hey, doesn't seem hard, but then again, I'm kind of antisocial anyway. I like you. I like all of you. I love my students, but I'm not big on going to big crowds and gatherings, man. Every time I've been go to a Brewers game or go to a theme park or go to the zoo or go somewhere, the big crowd or there's lots of people, and in the past, it just seems like, seems like you always end up with something. So usually a headache, but sometimes it's yeah. But anyway, yeah, man, you gotta get the curve has never flattened. It just keeps going up and up and up. And so anyway, um, yep, losing it. Bring it, reeling it back in. Uh, Mainly because we're in the home stretch. This little section here, again, we're not going to discuss all of these vessels that feed the outside of the heart. We do that next semester. You've probably heard of bypass surgeries. These little coronary arteries sometimes can get clogged, so we have to figure out a way to bypass them. But again, we're not going to discuss anything with this stuff. Oh, we were talking about dissections and this damn COVID and pig heart. So yeah, we dissect brains, we dissect hearts, we dissect kidneys, we dissect intestines and stomachs, and yep. So, well, next semester or any semester, if you're ever on campus at Elkhorn and I'm over there and you're there, stop in. I can pull them out and show them to you. We've got them in the lab all the time. So anyway, we'll look at these two slides. We do a lot with next semester again when we're studying some of that stuff. Yeah, I would imagine so. Go to it's called Carolina Supply or Carolina Biological. Yeah, that's who I would start with. Carolina Biological and Wards, WARDS. I find that Carolina has the best stuff, reasonable prices. Yeah, you can get a sheep, you can get sheep brain, you can get dissection kits, so you can actually get, you'd get like a sheep brain kind of vacuum sealed, and then it would come with like a little kind of like a placemat with like a map. It's like a map of the sheep brain, and then you can even get a little kind of like dissection kit with it, and they're reasonable. They may be $12 to $25, so anyway, yeah, something to look into. I don't know if you need like an institution disc, like connection. I doubt it. You might be able to find them on Amazon. seems kind of weird, but I know they sell models on Amazon. We're getting the girls are getting um, the Mr. Torso models that we have at school with the organs that come out. They sell, like 18-inch ones and 24-inch ones. So anyway, yeah, getting my 13-year-old and of course the 7-year-old. But yeah, they'll share it, but as one of their tools for learning. A little Mr. Torso or Ms. Torso, I don't know. Just the torso. Okay, so anyway, here's the musculature again. You can see the thickness of the ventricles, left ventricle, right ventricle. One thing you may want to do too, we're in Wisconsin, right? It's probably deer hunting season. I guarantee if you know any deer hunters or know someone who knows a deer hunter, some of them go after all the meat. They go after the organ meat and the actual, so obviously the muscle, skeletal muscle. But some of them I've had students bring in lungs, deer, bring in a whole thing of deer lungs, deer heart. So that's another way of doing it. You could even go to your probably not Walmart, but like like Piggly Wiggly, maybe, I don't know, like an actual, like a butcher shop, and you might be able to get some, get organ meat that way, like cow heart or something. Yeah, absolutely. Yeah. 1550 Carolina, Carolina.com. There you go. Carolina. So if I think so it's although it's Carolina, right? Carolina. So yeah, 1550 on Amazon. All right, Carolina.com. Yep. Well, you wouldn't be doing it to preserve it, right? If you got it from like a butcher or something, you'd be getting fresh, and then you would want to refrigerate it. You could dissect it, over a week or two period of time, and then throw it out. But yeah, if you're wanting something that you don't have to worry about that's got preservative, yeah, that's been preserved, sure. And at that price, 1550, you're not gonna be able, you can go to a butcher and ask for sheep brain. It'd probably be more than that. I mean, I don't know. So yeah, awesome. Well, yeah, well, that's the other thing too. Yeah, if you actually got cow heart or deer heart from, a butcher, you can eat that. You definitely do not eat what comes from Carolina Supply because that's got preservative in it. Um, you probably know that already, but anyway, yeah, sheep brains. We do sheep brains at school. They're reasonably priced, as you can see. Yeah, 1550. Hearts are probably closer to $60 a piece, maybe 40 to 60. They have pig heart and sheep heart, or pig heart, cow heart, maybe sheep heart. They have a sheep GI tract from mouth to anus too. I think that's closer to like maybe $150. But anyway, yeah, they've got all kinds of stuff on there you can order. Let's see. Almost done. The only other thing I wanted to show you guys internally with the heart, a couple of structures that again, if we were to dissect, this is kind of what we would see. But there are what are called little papillary muscles, little bumps, and then what are called chordae tendineae. So I'm going to go back to this one, but you can see these valves are connected to little cords, and these cords are called chordae tendineae, and then they're connected to little bumps. And we've seen the word papillary before. We already know papilla or papillary means bump. So these are very, so my point is the inside, the lining of the ventricles is very ridged. There are a lot of rugae, a lot of bumps, grooves, canals, caverns, and certainly these papillae are these little bumps. Yeah, nice. Yep. Yeah, that's super cool. Yeah, if you can get a hold of fresh lungs, a fresh set of deer lungs, pig lungs, um, even with it, even if you take what we do in class is I don't have intubation tools in my A&P course, but I do have glass pipettes. So they're basically big long glass straws. So what I would do is put the glass pipette down in through the trachea and then close it off, and then I'd inflate the lungs so you can palpate them. They feel really wild. They're so spongy and neat. But cards pull the valves with the electrical conduction. Yes, in essence, they're kind sort of. Yep. So that's I'm just gonna give you just the names of them. So for now, yeah, because we're not going to do anything with electrical conduction, but in essence, well, next semester when we get into how does this work, how does the heart function, it's such a big deal. That's why we do spend a lot of time on it, a couple of weeks just on heart beating, heart rhythms, the electrical circuitry, how the valves work. We talk about the pressure buildup within, and then we talk about blood pressure without. So yeah, we'll see these again. Absolutely, when it comes to the electrical circuitry and how we get these. So in essence, well, I do have. It's kind of a teaser trailer at the end here. So there we go. So I've got these valves or these slides, and they show kind of what's going on. So look at the lower right. So look down here for now. So yeah, you can see the mitral valve, which is the left AV valve, has these chordae tendineae attached to the papillae. And so when that valve is open, the aortic valve is going to be shut because we're filling, the ventricle's empty, so we're filling it up. Blood was in the atrium. So basically, so notice now the valve's closed. So the ventricle is just contracted and it's ejected blood into the aorta, right? You can see that. And so now what's going to happen is, so we just had an electrical signal, right? That's what causes it. So the electrical signal comes and then the muscle contracts. So that's what just happened. Bzz, we gave it a little jolt of electricity and it just contracted. So now we're kind of in between stimuli or in between jolts of electricity. And so the heart is kind of relaxing a little bit. And so as it's relaxing, so notice these papillae, as the heart's relaxing, plump, the papillae relax with it. And as they relax, they kind of pull those puppet strings and then opens up the mitral valve, and then the blood leaves the atria and drops down. So it's almost like a trap door, right? You've got the top floor, the atrium's filling and filling and filling. We've got the door shut. And then once this bottom room's empty, now we can open the trap door, and then all that blood. And there's a little bit of electrical impulse as well at the roof of the atria. So the atria also give a little bit of a squeeze or a little bit of a contraction to get that optimal blood leaving the atrium and traveling down into the ventricles. So yeah, you can see that kind of back and forth, how the ventricles are contracted here, and then as they relax, they kind of pull those. You can see the way the positioning of the papillary muscles kind of relax those and allows that that mitral valve to open. So when they're tensed up, from the contraction, you can see that valve's closed. And plus, we'll see next semester there's a pressure too that's pushing against that. So pressure's going out this way, but there's also pressure pushing against there that helps to keep that shut. So yeah, you can see the bicuspid, two cuspid, tricuspid, three cusps. Okay. So yeah, there's an electrical circuitry system that comes from the vagus nerve and travels to the pacemaker. Again, all of that stuff's for next semester. They don't want us even really discussing anything to do with electrical conductivity of the heart. They don't want us getting into that yet. They don't want us getting into the blood supply network of the heart itself. So the coronary circulatory system. Yeah. So that's it really for heart structures. Next week we're going to go a little bit further and look at all of these blood vessels we've already seen some, right? We've seen the two vena cava, the inferior and superior vena cavae, I think is technically the plural, and then we have the aorta. So we've seen a couple, not very many, right? So next week we're gonna, and it's of course the pulmonary stuff, right? Pulmonary arteries, pulmonary veins. So we really only looked at four major vessels today: the two vena cava, the aorta, and then the pulmonary arteries and pulmonary veins. That's it. So we have more to do next week. We're going to look at, well, first thing we'll do on Tuesday is look at the basic differences between an artery, a vein, and a capillary. Well, we've discussed that a little bit. We know that arteries always go away, veins always go towards. So we'll go a little bit further with that. But we're going to look at kind of the internal structures of, we'll look at the linings, right? Because these are tubes. So we're going to see epithelium lining these tubes. We're going to see connective tissue deep to that. And then we're going to see a little bit of smooth muscle involved. So a lot of layers, just like all the tubes we've seen. Well, actually, we haven't really seen a lot of tubes yet. So this is kind of going to be your first real introduction to the anatomy of a tube, which is good because the rest of the semester is a lot of tubes. So we do respiratory's got tubes, digestive has tubes, urinary has tubes, reproductive has tubes. Thankfully, they all pretty much have a similar structural makeup to them. So anyway, I'll introduce you to the makeup of a tube, the lining, the epithelium, connective, and muscle involved, and then we'll look at the differences between arteries, veins, and capillaries with those linings and the construction of these tubes. And then let's see, then we'll name them. We'll give you some specifics, and most of these arteries and veins are going to be named for where they're located. So you guys have a pretty decent have had pretty decent exposure up to this point to some body regional terms. You know, brachial means arm, you know, femoral means femur, you know that hepatic means the liver, gastro means stomach, and so on. You guys know some of these body terms. Nerves are named for these body regions. We're going to see arteries and veins as well. We'll look at a couple, of course, oddballs. You already know of a few, right? The carotid artery and the jugular vein in the neck region. Those are kind of odd names. We'll look at the longest vein in the body, has kind of a weird name as well. But for the most part, arteries, veins, generally named pretty much follows in line with what we already know. Capillaries aren't really named, so that's good. We don't have to worry about that. So then we'll leave that. So we won't get into blood pressure, anything like that. We're just going to name some arteries and veins. And then from there, we're going to look at the immune system. There's just a few structures with the immune system. We'll analyze those a little bit, look at lymph nodes and lymph vessels and lymph fluid a little bit. We'll look at the thymus gland in a little bit more detail. We'll look at the spleen a little bit, maybe the tonsils, but that'll be it. We'll do all that on Tuesday, and then Thursday we'll do a lab. So next Thursday we'll kind of put all of this together. We'll look at your lab portfolio activity. We'll go through some of that. You'll break out and work on some of that together. There's a blood typing activity in there. There's a lot of labeling in there as well. So pretty straightforward, and I think we could probably get pretty well done with Unit 8 next Thursday. But if not, we'll take it into the following Tuesday of Thanksgiving week. week. But either way, that's all I have tonight. So you guys take it easy and stay warm. You've got plenty to work on. And if you have questions, again, please email me and let me know if you have administrative questions too. I can help you, may be able to help you with those as well. And again, I may not know the answers, but